All right, I'll wait another minute or two. Okay, let's get started. First of all, I want to talk a little bit about the follow-up to the last problem set. On the first problem, I said, given that the divergence of a vector field equals 0, is it possible that f equals the gradient of a scalar field? That was the question. Now, some people said things about the curl of f, and of course the curl of f will be 0 if f is the gradient of a scalar field. And then you could ask, is it possible for both the divergence and the curl to be 0? And the answer is yes. There are plenty of fields that have 0 divergence and 0 curl in some region of space. The electrostatic field is a good example of such. The electrostatic field in free space is a good example of such a field. All right, so we can have 0 divergence and 0 curl. Now, how do we show it? Well, let's see here. If f is equal to the gradient of s, del dot f is going to be equal to del dot del s, or del squared s, which is partial squared s partial x squared plus partial squared s partial y squared plus partial squared s partial z squared equals 0. Some people just said, yeah, it has to satisfy that equation. Others start saying, well, they would give examples. Now, if the example you gave was a constant, what if s is a constant? That's a trivial example. I gave you a few points, but if s is a constant, then its gradient is 0. So all you've really proved is that this works for a 0 vector field. And 0 is usually an important exception or an important trivial case. The question in physics is usually, are there non-zero solutions to this equation? If there's a non-zero solution to an equation, then that means that something is happening. All right, some people would produce a solution that's a little more interesting. Say s equals ax plus by plus cz. And if they produce that and show that it satisfies the equation, and they use the construction of a solution to prove the existence of solutions, that's fine. Constructing a non-zero solution does prove that non-zero solutions exist. But if you constructed that solution, said it must be of this form, all right, well, no, it doesn't have to be of that form. There are actually plenty of solutions to this equation. When you take E and M, you're going to spend most of a semester studying solutions to that equation. There are many solutions to that equation. So if instead of just saying, here's one non-zero solution, it exists, therefore non-zero solutions exist, great. But if you said, oh, the solution must be of this form, well, no, it doesn't have to be of this form. Here's another solution. S equals a constant times x, y, z. Take any of the 3 second derivatives, and they're all 0. You add them up, you get 0. Here's another solution. S equals e to the ky minus I z. Because the second derivative of s with respect to y is k squared s. The second derivative of s with respect to z is minus k squared s. And the second derivative with respect to x is 0. Here's another, and we could have mixed around the x and what we could have replaced y with x or z with x or added in another term involving x. We'd have to change the exponents slightly. But the point is that we could certainly do things like that. Here's another solution. S equals x squared plus y squared minus 2z squared. Some of you gave that solution. That's another valid solution. And I could keep on constructing valid solutions all day. So again, if you wrote down a valid solution and said, see, non-zero solutions exist, great. If you wrote down a valid solution and said all solutions must be of that form, I couldn't give you full credit. Any questions on that? If you wrote down solutions like, if you wrote down a solution and you thought it was the most general solution, even though it isn't, I still gave you half credit unless it was a constant solution. But if you got that far, even though you were mistaken, I still gave you half credit. That's fine. You got most of the way. Now here's the one that bothered me. When people started saying things like the gradient of a scalar function, they usually did this with phi, or so I'll write it the way most people wrote it. The name itself doesn't matter. They would say that's partial phi x, partial x, x hat, plus partial phi y, partial y, y hat, plus partial phi z, partial z, z hat. This is wrong. Please do not copy it down. Please do not come to me after class saying, hey, you wrote that down, but I think it's wrong, but you wrote it down, so I guess it's right, so can I put that answer on the test? Please don't do that. What's wrong with this is that phi is a scalar. I.e., one number. Now it's a scalar field, so it's it could be a different number at every point in space, but still at every point in space, it's one number, not 3 numbers, one number. And that's a very important distinction between a scalar and a vector. And that's a really important distinction that you have to be comfortable with in physics. And now that brings us to important distinctions of getting used to things in physics. That brings us to Friday. Let me first say that, yes, I got impatient on Friday because I thought that certain things had been done before. All I can, and I apologize for getting impatient. All I can say is that my frustration is not actually with any of you, but for some of you, meaning that if you don't get certain things down, the basics of the first 2 years of math, then upper division physics is hell. And I don't want upper division physics to be hell for you. And I don't want to see people put their time into that. I would either rather see people get that down and be okay in upper division physics. I really hope that everything I'm doing right now, you will see in the next 3 semesters in your other classes. I really hope that what I'm doing right now is going to make the next 3 semesters manageable. Or if you're not getting it down, and that just isn't in the cards, then I hope you find another path. And I'm not saying that because I want to chase people away. I'm saying that because life is short and you should find the right path. And I could just keep cashing your tuition checks, but cashing your tuition checks, if it's not working, cashing your tuition check doesn't feel like getting paid to help people. It feels like collecting 30 pieces of silver for those who are familiar with a certain famous book. And I don't want to collect 30 pieces of silver. But let's talk a little bit about the differential element of area on the surface of a sphere. I'm going to draw it bigger. All right, so we're looking at a little area element on the surface of a sphere. Now this distance is r, this distance is r. If here we're at an angle theta, then here we are at theta plus d theta. So this is d theta. So this arc length here would be r d, you'll see what I'm going to put on the other side. It'll be r d theta. That's how big it is along that direction. Then we've got this other direction. And again, the distance swept out is going to be the radius multiplied by an angle, and that angle is going to be d phi. But now the distance here is the distance from the axis, and the distance from the axis is r sine theta. So this distance here will be r sine theta d phi. And when you put them all together, you get that dA is equal to r squared sine theta d phi. So whenever you're integrating in spherical polar coordinates, your element of area is this. And the direction of the normal vector from that, the normal vector points in the r hat direction. So dA vector is r hat r squared sine theta d phi. Any questions?
So if we had a sphere with a radius, let's say big R, it wouldn't be little r squared, it'd be big R squared.
Yes, because that which we call r would by any other name still be the radius of the sphere. Anything else? I could call that radius m because I decided to call it the Montague sphere. And that which we call a Montague would by any other name still be the radius of the sphere. Anything else? Okay, well, let's start new material. Let's start Fourier series. We're going to be talking a lot about periodic functions. Periodic functions are important in physics. They're important in physics because even things that aren't periodic can be broken down often into waves which are periodic. Plenty of things are periodic. A pure note in music is periodic. And even if a pure note is not what any violin actually produces, even if a song is a mixture of pure notes, still, it's made out of pure notes. Plenty of materials are crystalline. And people will say, well, you know, in reality, few materials are fully single crystal. Yeah, but material could be crystalline for several nanometers. Several nanometers would be dozens, hundreds of bond lengths on a side. So for several hundred, you could have hundreds by hundreds by hundreds, that could be millions. So you could have something that's periodic for quite some time. The solutions to the Schrodinger equation would be periodic there. Plenty of important optical devices are periodic. Gratings, which are used all the time in spectrometers, photonic crystals. So periodic systems show up everywhere. And the beautiful thing about periodic functions is that no matter how complicated they look, you could have something that looks like that. I don't know, to my non-expert eye, this looks vaguely like a heartbeat. This looks vaguely like what you see on heart monitors, okay? You could decompose a heartbeat into things like that. And by the way, medical signal processing uses tons upon tons of Fourier analysis. This is really complicated. This itself looks nothing like a nice steady sine wave, all right? But even though it looks nothing like a nice steady sine wave, it turns out that any function, any periodic function that is one single valued, that means that in the language of high school algebra and pre-calc, it passes the vertical line test, that for each value of the input, there's one well-defined output. And you might be thinking, isn't that the definition of a function? And generally, yes, but things get a little more complicated when you start dealing with certain things in complex analysis that we're not going to cover in this class. But if it's single valued, has a finite number of peaks in each period, move this out of the way, and peaks and troughs, and a finite number of discontinuities. And the integral from 0 to the period of the absolute value of f of t dt is finite. If it satisfies those conditions, then we can write it in something called a Fourier series, which is f of t equals a0 over 2 plus, and we'll explain what each of these coefficients means. Any periodic function that satisfies these conditions can be written in terms of just a bunch of sines and cosines. And all of those cosines, they all have a frequency that is an integer multiple of what we call the fundamental frequency. N times 2 pi over t, or 2 pi f times n, n times the fundamental frequency. So you can take something that's periodic and you can break it down into a sum of things that all have the same period. And you may be thinking, wait, they all have the same period? Well, yes and no. Here's our fundamental, right? Here's our lowest frequency. Here's the period t. This next wiggle, which I meant to do in a different color, technically you could say that its period is t over 2. But of course, if I go out a distance t, it has indeed repeated itself again. So in some sense, it still has the same period, right? Its frequency is a multiple of the fundamental frequency. Now let's talk about what these different conditions mean. Single valued just means that our messy function, I'm going to write something like this, that passes the vertical line test. That for any value of t, there's exactly one value of f. Finite number of peaks and troughs in any period. There's a peak here, a trough there. That's basically excluding things that have infinite numbers of wiggles in one period. And you may be thinking, does something with an infinite number of wiggles in one period even make physical sense? Well, it does when you start getting into fractal geometry. And we're not going to do fractal geometry in here, but all that means is that some of this math does not carry over to fractal geometry, or you have to be much more careful in fractal geometry. Finite number of discontinuities. This is one of the few places in math where we're okay with discontinuities. In fact, one of the most important functions in Fourier analysis, the square wave, is discontinuous. We're going to spend a lot of time in Fourier analysis talking about functions that switch between plus and minus 1. In electrical engineering, it's very simple. It's flipping something on and off. And you might say, why plus or minus 1 instead of 0 and 1? Well, sure. But if we wanted to have 0 and 1, then we would just take 2 times our square wave minus 1, because 2 times would, 2 times our square wave, plus 1 over 2, my bad. Square wave plus 1 over 2, because adding 1 would shift everything up. And then we divide by 2. And for some reason, it's not letting me, there, now it is. Then we divide by 2, oops. When we divide by 2, that goes back down to there, that stays there, that goes back down to there, that stays there. All right, people will work with it either way. We're just going to do something convenient a little bit later on. So we are allowed to work with discontinuous functions, which means switching things on and off, as long as there's a finite number of discontinuities. Again, you could have functions that have an infinite number of discontinuities in a finite interval. Mathematicians deal with those in real analysis because those are sort of outlier cases for their theories about continuity. We're not going to worry about them. Physicists do worry about such things when we get down to fractal geometry, which is important in nature, but again, we're not going to worry about it here. We can't teach all of physics in one semester. Any questions so far? One nice practical thing about this is that often, even though this has an infinite number of terms, often the first few will suffice. Not always, but often. It's a bit like a few weeks ago. Remember when we were plotting some Taylor series in Mathematica? And I would plot a couple terms of the Taylor series, and the Taylor series would match up with the function really well. And then I'd add in a few more terms of the Taylor series and would match up even better. That's one reason why we care about this. Another reason why we care about this is that it's going to turn out that this makes it really easy to compute the energy stored in periodic functions. Remember how we worked with Legendre polynomials a few weeks ago? And I showed you that if you write a function in terms of Legendre polynomials, then you square the function and integrate it. The integral of the squared function takes on a very simple form. Well, something similar turns out to hold when you work with Fourier series, which is very useful for calculating the energy stored in some sort of periodic disturbance. Now let me show another example. This is a program that I use to calculate the motion of a pendulum. And when you learned about a pendulum in intro physics, they probably told you that a pendulum is just a sinusoidal wave. If you make a small angle approximation, then the period of the pendulum is 2 pi square root of pendulum length over g, and it's nicely sinusoidal. That's true as long as the starting angle is small. But here, this rise is pretty steep, remains kind of flat. This is not perfectly sinusoidal. And for the values of L and G that we put in, the period, if we were working in the small angle approximation, would be 1. But because we're very far from the small angle approximation, the period is much longer than 1. And so the frequency is 1 over the period. The frequency should be less than 1. Now here what we have is we have the spectrum of this motion. Don't worry about what I'm plotting here. You may be thinking, why isn't the energy constant? It's because we're making certain approximations that don't quite work. But ignore this. This is something we would talk about in depth in computational physics. Just look down here. Here you see the spectrum, okay? It basically takes this oscillating function and breaks it down into waves of different frequencies. And we've got a big spike at a frequency that's less than a half. And well, the period, it starts here, gets back around there. So the period is around 3. And sure enough, the peak is around 1/3, give or take. But then if you look at a somewhat higher frequency, you see another peak. I'm going to zoom in on that. You can see another peak here and another peak there. And this peak is at 3 times the fundamental, not twice the fundamental. It turns out that there is no contribution at twice the fundamental frequency, but there's something at 3 times the fundamental frequency. And there's something at about 5 times the fundamental frequency. And if we zoom in even more, we might see something at 7 times the fundamental frequency. You can sort of see a peak here, which turns out to be at 7 times the fundamental frequency. And so Fourier analysis enables us to see how much things deviate from a simple sinusoidal motion. I'm going to make those sharper. It turns out that if you run this for a longer time, the data comes out sharper. Multiplied the runtime by 100, so, okay. Now you're thinking, well, what's really going on up there? What's going on up there is I've plotted so many cycles of oscillation that you can't see anything. But if you zoom in on it, you see something. Then we look at the spectrum, and everything is much sharper because basically we collected more data. And sure enough, we see something at a frequency of about 0.35. And 1.05 is 3 times 0.35. And 1.7 something is a little more than 5 times 0.35, but that's to be expected. And then we can zoom in there and we can see additional peaks out here. And maybe if I were to zoom in, I might see one more. I could persuade myself that there's a blip on there, but it wouldn't mean much. Yeah, we're not seeing much. Anyway. That's an application of Fourier analysis to figure out whether something is obeying a very simple law in the small angle approximation, or if something is a combination of several frequencies. And so you can see it in the motion of a very simple visualizable system, the pendulum. Let me give you a very practical experimental application of Fourier series. So have any of you ever played with a lock-in amplifier? All right, I'm seeing some heads nod. So a lock-in amplifier, what it does is it looks for a modulation of the signal. Because you could imagine that you're collecting light from an object, all right? You're shining light on an object, and then you're collecting the fluorescence that, well, if I'm gonna do this, let's do this right. We shine blue light on an object. It fluoresces red. All right, but let's say that the fluorescence is weak. If the fluorescence is really weak, then background light could overwhelm any fluorescence that you're going to see. So what people will do is they will modulate the blue light. You could basically put a fan in front of the laser beam. Okay, you just put a little fan blade in front of it, and then the chopper wheel on the fan blades, you know, will block the laser beam and then unblock it and block it and unblock it. And by blocking and unblocking it, you're modulating the signal. You're modulating it a certain number of times per second. Well, this thing is only going to fluoresce when there's light shining on it. And yes, technically it'll be fluorescing probably a few nanoseconds after the light shines on it. But if you're blocking the beam 1,000 times per second, the illumination is milliseconds. Nanoseconds are a millionth of that. So we don't really have to worry about those delays, all right? So the only signal that matters is the signal that's at the same frequency as the modulation of the blue light coming in. So people will just collect, will collect the red light with a very fast photodiode, a photodiode that can respond very quickly. And then they'll Fourier transform or take a Fourier series of the signal in the photodiode. And the background light from the room will be coming in at all times. But the red fluorescence will be oscillating at the same frequency as the incoming light. And so they look for that, just like looking at that spectrum in the simulation that I showed you. One more example, there are people who look for deviations from Newton's law of gravity. Newton predicted that the gravitational force between 2-point objects goes as 1 over r squared, 1 over the square of the distance between them. So they'll have some big mass. I mean, there's already a giant rock beneath their lab. It's about 6,000 kilometers in radius. But besides that giant rock, they'll have some other very large mass. And what they'll do is they'll have that mass spinning, all right? And spinning, they'll have, the mass will be spinning, and it's usually also made with some holes in it, okay? And because it's made with some holes in it, this is the Etvash research group at Washington. I saw a seminar by them a long time ago. They make something, they come up with a shape that has gaps in it, okay? So the gravitational signal that it produces, the gravitational field that it produces will oscillate as the thing spins. If the shape were perfectly homogeneous, spinning wouldn't change the mass distribution that you see. There'd be some very, very subtle relativistic effects, but those might not be detectable with this equipment. But if you put holes in it, like a Swiss cheese object, okay? So mass, hole, mass, hole. And no, I'm not trying to make a New England joke. Mass, void, okay? If you spin it like a wheel, then the gravitational force will oscillate. And then they just look for a signal that's oscillating at the same frequency as they're spinning. And that way, they can separate out stuff in the environment. So it's a very common thing in experiments to have a modulated input and look for a modulated output, because your background won't be modulated on the same way that your input signal. And so anything that's modulated at the same frequency as your output signal must be a response to your input. And all of experimental physics is that in some sense, an input-output relationship. Shine light on this, see what happens. Vibrate this, see what happens. Subject it to a force, see what happens. Put electrons into a different energy level, see what happens. All right? So whatever stimulus they apply to their sample, whatever stimulus they apply to their physical system, they just look for a response at that frequency. Questions?
So the lock-in amplifier, when you do have some periodic frequency, is that what the lock-in amplifier is amplifying?
Yeah, it's supposed to amplify one particular frequency. If you're modulating your input at 1 kilohertz, then it will take any signal it gets at 1 kilohertz and amplify it. And any signal that isn't at 1 kilohertz will either be left alone and not amplified, or maybe actually attenuated, discarded. But either way, the signal at one particular frequency gets amplified. Other questions? I see there's something in the chat. Okay. The last thing before we start actually calculating these coefficients is I'll just go over some of the other notations. There's a number of notations that people use. We're going to keep on saying A0/2 for the constant term, just because it makes certain things that come later much easier. But you will see, instead of n equals 1 to infinity. All right, an cosine, like I said, 2 pi nt over the period plus bn sine 2 pi nt over the period. Or some people will write this as 2 pi mu naught times t, where this is nu, a Greek letter that looks just like V. But it's not, it produces endless confusion. Or 2 pi f naught, there should be an n there, 2 pi f naught nt you'll see n omega t. I usually prefer this notation just because there are fewer symbols to carry around. You will see 2 pi nx over L, or nkx. I like this notation and this notation. As for figuring out which notation to use, I don't really care, as long as you're consistent and it's clear. And you should be prepared for any of them in the same way you should be prepared for the possibility that instead of saying a mountain lion, someone will say a cougar or a puma or a panther. Instead of saying soda, they might say pop or Coke, and you just have to deal with it. Or in some places, fizzy drink, and you just roll with it. All right, let's start calculating some of these. The way we calculate Fourier coefficients is via inner products, because these coefficients are, in a very real sense, just like vector components. You know how Vx is x hat dotted with the vector V? And remember how we said when we expand a polynomial or approximate a function with Legendre polynomials, CL, PL, we said that CL is equal to the inner product PL star of X, F of X, dx minus 1 to 1. And we only did that for finite numbers of polynomials, so up to order 3. Well, we can do something very similar, and I'm going to prove to you that it works. I'm going to assert for now that n greater than 0. Here's how we're going to compute an. We are going to find the inner product of cosine n omega t with our function f of t. So we will integrate 1 over the period from some time t naught to t naught plus the period. And you're thinking, what's t naught? Well, it can be anything because this function is periodic. So it doesn't matter where we start from. Wherever we start from, if we go forward 1 period, the function will repeat. And you showed on the assignment due today that when we're integrating products of sines and cosines or complex exponentials, that it really doesn't matter where we take our starting point. So we're going to integrate cosine of n omega t times a naught over 2 plus the sum, and now I have to use a different name for the labels, m omega t am cosine m omega t plus bm sine m omega t dt. And let's think about what will happen, because we're going to multiply the cosine by a constant, then we're going to multiply the cosine by some other cosine, then we're going to eventually, as we go through these terms, m equals 1, m equals 2, m equals 3, etc., we're eventually going to get to a term where m equals n. Then we're going to multiply cosine of n omega t by all of these sines. So let's just do all of the cases. 1 over t actually, let's leave out this 1 over t for now. This 1 over t does not yet matter. We'll just leave it out. Integral from t naught to t naught plus the period a naught over 2 cosine n omega t dt. Assume n is greater than 0. If n is an integer and we integrate a cosine times a constant over a full period, what do we get? It's been on multiple assignments.
0.
0. Now, if we were to do a naught, now let's consider m equals n. an cos squared n omega t from t naught to t naught plus the period dt. We're going to use a trig identity. That's going to be the integral of 1 plus cosine of 2n omega t over 2 dt. And the integral of the second term, well, we're just integrating a cosine over its period. So that integral is 0. And so we're left with an times t over 2 evaluated from t naught to t naught plus the period equals an over 2 times t naught plus the period minus t naught equals an over 2 times the period. Now, I would like to conclude that this is the only non-zero term, but we can't conclude that yet. We have to actually show it. Let's consider anything else. Let's say that m is not equal to n. So we've got the integral of cosine n omega t, cosine m omega t. There should be an am in here. All right, we've got a product of cosines. Integrating a product of cosines, we could just invoke some trig identities, but I would rather think this out in terms of complex exponentials because you just did some integrals of complex exponentials. We're going to have e to the I n omega t plus e to the minus I n omega t, e to the I m omega t plus e to the minus I m omega t, whole thing over 4 because each of these cosines has a factor of 1/2. So we get 4 terms in here. We're going to have e to the I times n plus m omega t plus e to the I n minus m omega t plus e to the I, and then multiply these two, m omega t minus n omega t, plus e to the minus I n plus m omega t, whole thing over 4. All right, we've got a whole bunch of complex exponentials integrated over a period of oscillation. But let's think back. What do they integrate to?
Zero.
0, yeah, because these are periodic functions. So when we integrate them, the antiderivative is also periodic, so it's the same at one end of the interval as it is at the other. Now we also have to integrate cosine n omega t with all of the sines. So now we've got the integral from t naught to t naught plus t of bm cosine n omega t sine m omega t dt. Well, if m is not equal to m is not equal to n, we're going to have e to the I n omega t plus e to the minus I n omega t times e to the I m omega t minus e to the minus I m omega t, whole thing divided by 4i. And again, we're just going to get a whole bunch of terms that look like this and this and this and this. Some of the prefactors will be different. You know, instead of a plus sign, we might have a minus sign or a minus I or something. But all of these things integrated to 0 before, and they still integrate to 0. Any questions on that?
So since this is an inner product, does that mean they're all orthogonal to each other?
Yep, it means the cosine of n omega t is orthogonal to cosine of m omega t, where m is not n. And cosine of n omega t sine of m omega t equals 0. And no matter what, but I'm implicitly assuming that n and m are integers. If they're not integers, all bets are off. But if they're integers, then this holds. Now I haven't case that n equals m, because if n equals m, then some of these difference terms become, well, the differences up here become 0. But those difference terms, the easiest way to show it is to just explicitly calculate the integral of sine n omega t cosine, n omega t dt. And that is the integral of 1/2 sine 2n omega t dt. And this integral is 0. Because again, we're taking a sinusoid and integrating it over its period. So that integral has to be 0.
So I get the sines and the cosines being orthogonal, but I'm trying to think of when you change a cosine frequency, how does it become orthogonal, like graphically?
Graphically, I think graphically the easiest way to do that is for me to switch to Mathematica. So I have a Mathematica file for something else, but I'm just going to put in at the top, we'll just put some stuff in here. Let's plot, I'll say m equals 2, n equals 3, plot cosine of 2 times pi times m times t times cosine of 2 times pi times n times t, t going from 0 to 1. And this function is positive half the time and negative the other half the time. If it helps, I could take it over 2 periods. And whatever it's doing up here when it's positive is the mirror image of what it's doing down here when it's negative. You can see how there's this little bit sticking down where it's mostly positive, but there's a little bit sticking down. Then you go into the part where it's mostly negative, and there's this little bit sticking up. Visually, the positive and negative parts are the mirror images. Does that help?
Okay, yeah, thank you.
Mm-hmm. Anyone else? We could change it around. We could go to other values of n and m. And no matter what we do, we get something that is, that one is far from obvious. That one is very, very far from obvious. But if we can see that it's tall and narrow here and shorter but wider down here. And it may not be obvious, but then we have to go back to the algebra. Any other questions?
I mean, I understand that when we take the inner product of these two functions and we get 0, they are orthogonal. But I mean, I understand that when we take the inner product of these two functions, they are orthogonal.
But
I,
no, I said but where's the but? I get the.
oh, okay. But why do we care? You know, I'm still trying to digest, like, is this really just a fun fact, or does the inner product being 0 has, or it being orthogonal have any more significance?
What it means is that when I take the inner product, if I just take the inner product of two functions, well, that in and of itself isn't of huge significance, but the integral from t naught to t naught plus t of f of t cosine n omega t dt is equal to t over 2 times an. So that orthogonality means that when we integrated, everything went away. All of the coefficients went away except for this one.
Right. Okay.
That's what it means. It's just like if I were to take x hat dotted with vx x hat plus vy y hat plus vz z hat. Well, x hat dot x hat is 1. Vx times 1 plus vy times 0 plus vz times 0.
Mhm.
And so we're left with just this coefficient. So a dot product is a way of getting vector components, and a more general inner product of functions
Right. I see.
is a way of getting coefficients.
Okay. Cool. Thank you.
We could do similar things for A0. All right, we would integrate, if we were to integrate just f of t dt, or if you want to be nitpicky, f of t times 1. We would get a naught over 2 integral plus the integral of that sum of sines and cosines. And we know that added up all those, that each of those sines and cosines on its own integrates to 0. So this goes away. And we are just left with a naught over 2 times t. So a naught is equal to the integral from t naught to t naught plus the period 2 over t f of t dt. Or if you wanted to be nitpicky, because of course cosine of 0 is just 1. And the only reason to write it out in this nitpicky way is that then we could say that an for any n is 2 over t integral from t naught to t naught plus t f of t cosine n omega t dt, and would even be true for n equals 0. And likewise for Bn, we could multiply by sine, multiply f of t by sine, and go through all the same arguments, using all the same orthogonality relationships, and we would get f of t sine of n omega t dt. Any questions? Going once, going twice. Then let's construct a Fourier series. Let's take the square wave. Which is +1, and then -1. And likewise out here. It just alternates between plus and minus 1, right? Now, let's see. This is an odd function, the way I've drawn it. Not everybody draws it as an odd function. Some people will do it like this. Now it's an even function. But even or odd, we're going to represent it this way. We can talk next time about what happens if we were to switch it to even. If I multiply an odd function like this by cosine, cosine is even, f of t is odd, so their product is odd. And we could pick any t naught we want. It would be very convenient to pick t naught equals minus t over 2. So we could do this from minus half the period to plus half the period. I could have picked something else. It's just convenient to visualize it this way. Odd times even over an interval that's centered on the origin. That has to be 0. Because odd times even is an odd function. And an odd function integrated over this interval has to give you 0, because down here the product, on this side the product is negative, on that side the product is positive. So that's a general fact. Odd functions have no cosine components. And even functions, which we'll deal with next time, turn out to have no sine components. So then I could integrate, I'm going to break this integral up from minus t over 2 to t over 2 of sine n omega t, sorry, sine n omega t times negative 1 dt and if you wanted to, we could be nitpicky and write this as multiplying by, oops, that should have been to 0, my bad. We could write this as multiplied by 1, but it doesn't really matter. All right, well, let's think about this. This integral here, we've got minus this integral. I'm going to do a u substitution. U is equal to minus t. U is minus t. It sounds like, I'm doing like a New York accent there. U is minus t, like a Joe Pesci character, like some 90s gangster movie. Anyway, u is minus t. T is minus u. dt is minus du. Sine of n omega t is sine of minus n omega u, which is minus sine n omega u. So if I put all this together, I've got 2 over, get that thing out of the way, 2 over the period, integral from minus t over 2 to 0. See how many minus signs we've got. We've got our negative 1 from the definition of the function, another negative 1 from du, and then another negative 1 from our substitution inside of sine. 3 negative 1s. We're left with another, just a negative 1, minus sine of n omega u du. Oh, and down here, u is now plus t over 2, my bad, because if t is minus period over 2, then u, or minus t, is plus period over 2. Any questions on how I did that? Last thing we can do. We could take this -1 and get rid of it by flipping the limits of integration. So we'd be left with 2 over t integral from 0 to t over 2 sine n omega u du plus 2 over t integral from 0 to t over 2 sine n omega t, oops. Hate this pen. And these are the same. We gave the variables different names, but there's my usual Romeo and Juliet speech about how changing the name of a variable doesn't actually change what's going on. The variable goes away when we're done with the integral. So this is 4 over the period, integral from 0 to t over 2, sine n omega t dt. And that was a lot of gymnastics, but what that enabled us to do was to simplify it, all right? To take an integral over the full period and turn it into an integral over half the period, using the fact that this function has an odd symmetry. It's negative on one side, positive on the other, and equal and opposite. So this is 4 over t. Then we take the antiderivative. The antiderivative of sine is minus cosine. And there's a 1 over n omega, evaluated from 0 to half the period. And so we're left with minus 4 over n omega period times cosine n omega period minus, well, cosine of 0 is 1. Oh, and that should be period over 2, my bad. Any questions on that?
Should that be a -8?
-8.
And in the numerator, because you, oh no, never mind.
Okay, so let's see here. Omega is 2 pi over the period. So omega t is 2 pi. So we're going to get minus 4 over 2 pi n. I'm going to make that a plus 4 because I'm going to do 1 minus cosine of pi n. And let's see here. If n is 1, if n is odd, cosine of pi n is -1. If n is even, cosine of pi n is +1. So cosine of pi n is -1 to the n. So what I'm left with is that Bn equals 2 times 1 minus -1 to the n over pi n. Any questions? Any questions at all? Well, I posted a file in Mathematica, which you are welcome to download and play with. What I do in this file is first I calculate the sine coefficients. I use the fact that it should be, is there a missing factor of, no, that works because I did a 4 over pi and then I did another division by 2 over here. So I've got 4 over pi divided by n. And then I've got this 1 minus negative 1 to the n over 2. I just wrote it out slightly differently. But we wind up getting the same thing. We get 4 over pi, 4 over 3 pi, 4 over 5 pi, 4 over 7 pi. If I wanted to go out to larger values of n, I just change n max, hit shift enter. But what I've got here is I've got a table or array of coefficients. And then I've got another command that takes that array of coefficients and it plots the sum of all those coefficients multiplied by sines. And then it also plots the square wave, which is what this is supposed to be. So let's play with this. All right, let's start with n max equals 2. If n max equals 2, well, we've got our square wave, and we just have a single sine wave. You might be saying, well, we went out to 2. Yeah, we went out to 2, except that only half of these have non-zero coefficients. So effectively, we've just got one sine wave. And we see that it's sort of kind of, I mean, it's definitely following a pattern similar to the square wave. But it's not matching up very well. Then we go out another 2, so we add another sine wave, and we see that it gets a lot flatter up here, and then it drops very rapidly, and it gets a lot flatter down here, and then rises very rapidly. It has the same period as the square wave that we're trying to approximate. We go out to 6, it looks better. Let's go out to 12. It's still wiggling in here. But you see how the approximation is getting better and better? That's just like what we did with Fourier series, where we found as we added more terms, it got better and better. Does anybody have a question? Let's go out to an absurd number of terms. Take a little while to plot. Okay. Anybody notice anything weird about this?
Those spikes on the edges?
Yeah, it's not, it doesn't look like it's quite converging to the square wave. It looks like it's overshooting here and then overshooting down here. What we're trying to do is we're trying to approximate a discontinuous function with a finite number of continuous functions. And approximating a discontinuous function with a finite number of continuous functions is not actually possible. You're always going to have some overshoot when you try to approximate a discontinuous function. And this is called the Gibbs phenomenon. Type that in here. Same Gibbs as Gibbs free energy, for those who have encountered that concept in thermodynamics. Not any real physical connection between the two things, although I'm sure if I thought carefully about some information theory concepts, I could make a link between the two, but it would be a very convoluted link. But there's no immediate link between the two, except in the way that all things in physics can be linked to each other with enough effort. But you're trying, it's just that he studied this, and you're trying to approximate something finite with something infinite, because you have an infinite slope right here. At the discontinuities, the derivative becomes infinite, or the derivative blows up. And so you're trying to approximate an infinite derivative, something that blows up, by adding a finite number of finite terms. And you can't really add up a finite number of finite terms to get something infinite. But if you try to do it, then you wind up having to get some pretty big numbers over here. Now, one thing that people might worry about is, hey, wait, I thought this is supposed to converge to the correct value. Well, yes. Anywhere that the function is continuous, the Fourier series will converge to the correct value. You might say, well, that overshoot isn't really the correct value. And I could hand wave and say something about the correct value at the edge. But let's zoom in a little bit more. Let's just look at the plot from 0.99 to 1.01. Okay, that's too narrow of a range. And then it's not quite what I expected. Okay. Now let's look and see what happens if I go out to 100. Now, before I hit Shift Enter, there's an overshoot here, okay? And of course, there's an undershoot there. I'm going to hit Shift Enter. I have my cursor where the overshoot was. You see how the overshoot moved to the right? As I add more terms, the new value over here, I mean, now it's a little bit of an undershoot, but it's a smaller undershoot than the previous overshoot. So as I add more terms, the value right here will get closer and closer. The value somewhere else will get farther, but then I can add even more terms, and the overshoot here would go down because the true overshoot would move, the peak overshoot would move to the right. And so at every point here, it eventually converges. It's just that there's some other point that will currently be further off, but then I add even more terms, and some other at that point will now get closer. And we're out of time. Tomorrow evening at 7, I'm having a midterm review session. On Wednesday, we will construct more Fourier series. Have a good day.
Thank you, Professor.
Yep. Thanks, Dr. Small.
Have a good day, Dr. Small.
Any questions, Marley, Ewan? I'm going to end the recording now.